So you've got two powerful robot arms, and you want them to work on one single task together. Sounds easy enough, right? Well, let me tell you, getting them to cooperate without just smashing into each other is one of the biggest hurdles in robotics. Today, we're going to dive into how you actually teach two arms to act like a single coordinated team, to pull off a job that neither one could possibly do on its own.
Okay, so here's the game plan. First, we're going to build a digital sandbox for our robots to play in. Then, we need to lay down the absolute ground rules so they don't crash. After that, we'll get into choreographing their movements, teach them how to do a cooperative handshake, and finally, we'll put it all together to see the main event, a perfect, synchronized pick and place.
All right, first up, before these robots can even think about moving in the real world, we need to build a perfect virtual replica of them, a place where we can simulate every single possibility. We call this the digital twin. And that's the million-dollar question, isn't it? How do you make that virtual copy, that digital twin, so perfect that it's indistinguishable from the real thing? Because if your digital copy is even slightly off, every single plan you make, every calculation, it's all built on a lie, and it will fail spectacularly in the real world. So, how do they pull this off? Well, it's a super clever divide and conquer strategy. You have two pieces of software working together. First, you've got Pinocchio. That's the brain. It's the math whiz handling all the complex calculations about the robot's joints and forces. Then you have MuJoCo. That's the brawn. It's the physics engine, the virtual world, where gravity exists, things can collide, and everything behaves just like it should.
Now, here's a really smart move from an engineering perspective. Instead of trying to wrestle with one giant, unbelievably complex 12-joint model for both arms at once, the system just simplifies the problem. It treats them as two completely separate 6-joint arms. This decision makes the math and everything else so much easier to handle.
You know, with two of everything, how do you keep it all straight in the code? It's actually dead simple, but totally critical. They use a strict naming convention. Every single component on the left arm starts with left underscore, and everything on the right starts with right underscore. It sounds obvious, but you would be amazed how important a small detail like this is for preventing chaos. Okay, so our virtual world is built. Now we have to deal with the most immediate problem. When you have two very powerful, very fast arms swinging around in a tiny box, the absolute first rule of cooperation is do not crash. So to make sure they're safe, the system is basically paranoid, in a good way. It's constantly running 4 different checks over and over. Is the left arm going to smack into itself? What about the right arm? Are they about to high-five each other into oblivion? And of course, is either one of them about to hit the table? It's watching everything. And here's the mind-blowing part. The system can run all 4 of those checks in less than 1 millisecond. That's faster than you can blink. By a lot. This incredible speed is what allows the robots to move so smoothly and confidently because they're not constantly pausing to wonder if they're about to hit something. All right, safety's covered. Now for the fun part, the choreography. This is where we go beyond just not crashing and actually get the arms to move together with purpose, like they're performing a synchronized dance. The big idea here, the real game changer, is something called the object-centric frame. This is a huge mental shift. Instead of thinking, okay, left arm, move here, now right arm, move there, you just focus on the object they're holding. It's like if you and a friend are carrying a couch, you don't think about your own feet, you think about getting the couch through the door. The box is the boss. And here's how that works in practice. You just define the path for the box. Simple. Lift it up, move it 30 centimeters over there, and put it down. From that one high-level command, both arms are smart enough to figure out exactly what their joints need to do at every single moment to make that happen. The result is this perfectly smooth, synchronized motion. And what's cool is that this symmetric mode isn't the only tool in the toolbox. The system can switch things up depending on the situation. For example, sometimes you need one arm to be the leader to get around a tricky corner. For that, it can use a master-slave mode. It's all about using the right coordination strategy for the job at hand. Okay, now we get to what is, for my money, the trickiest part of this whole thing. The moment those 2 grippers close on the box, the physics of the system totally change. They're not 2 separate robots anymore. They're physically connected through the box, creating a closed chain. And that introduces a whole new world of hurt if you're not careful. This is the classic problem. Have you ever tried to carry something heavy with a friend, and one of you accidentally pushes while the other one pulls? The thing you're carrying feels like it's about to be ripped apart, right? That's exactly this problem.
These are called internal forces, and they can build up and destroy an object without it even moving an inch. The solution here is just beautiful in its simplicity. It's called symmetric impedance control. Now, impedance is just a fancy word for how springy or stiff the robot arm feels. By programming both arms to have the exact same stiffness, if one arm accidentally pushes a little too hard, the other arm gives way by the exact same amount. The forces just cancel each other out. Problem solved.
Of course, you can't just have them be perfectly limp, you still need to actually hold onto the box. So, on top of that clever symmetric control, they add a tiny constant squeeze, just 10 newtons of force pushing inward. It's just enough pressure to get a secure grip without any risk of slipping. Think of it as a firm but gentle robotic handshake. Okay, quick recap. We've got our virtual world, we've got our collision avoidance, we've planned the choreography, and we've totally nailed the cooperative grip. Now it's showtime. Let's see how all these different pieces come together and watch the full pick-and-place pipeline in action.
The whole operation is run by what's called a state machine, which sounds complicated, but it's really just a to-do list for the robots. It walks them through every single step, one at a time. Okay, approach the box. Check. Grasp it. Check. Lift. Check. It methodically moves through every phase, carrying the box 30 centimeters, lowering it, releasing it, and backing away. And it won't move on until the current step is done perfectly. And the performance? I mean, just look at these numbers. They are absolutely incredible. The final placement of the box is off by less than a centimeter. The arms track their planned path with less than 5 millimeters of error. And that synchronized timing when they approach the box, they move within a single millisecond of each other. This is truly surgical precision.
So, what's the big takeaway from all this? It's that you can solve a ridiculously complex robotics problem with a couple of really smart, really elegant ideas. You don't need a super complicated solution. Just focus on the object, not the arms. And use symmetry to let the physics of the system take care of the forces for you. That is the magic right there.
Seeing robots coordinate this well, this precisely, it really makes you wonder what's next, doesn't it? What kind of jobs, what kind of challenges that are maybe too difficult or too dangerous for a person to handle alone suddenly become possible when you have a perfectly synchronized robotic partner. We're not just looking at a cool lab experiment here, we're getting a real glimpse into the future of how we're going to work and build together.